Hello everyone. In this video we are going to talk about edge detection, which is one of the early stages in computer vision and also in us. Edges can convey a lot of information. For most of the parts, the edges kind of show you the boundaries between the objects, right? Now, not all the time, but most of the time, the edges are where you can see object 1 separated from object 2 and so on. So they are absolutely a fundamental task that is done in our eyes and brain, and they help us basically go to the higher level task like object recognition and so on. Now, an edge basically in an image that is only light intensities is a sudden change in the light intensity level. So here, if you can plot light intensity versus the pixel position, you see you have a sudden drop, or it could be the other way around, a sudden increase in the light intensity level, right? And for example, it could be this way. So if you go from a dark area to a bright area, right? Or the other way around, go from a bright area to a dark area, then you definitely see a drop in the level of light intensity, and that represents this kind of step type behavior which shows an edge. And that you can see here in this picture inside the red circle or the red ellipse, especially in the ellipse when you go from a dark region to the white region, right? So the dark in here and the white in here, you clearly see between them an edge, right? So you see this white edge inside the red ellipse. Not always an edge represents a step type behavior. Sometimes an edge represents what we call a ridge. And ridge is you have like a dark area, then you go to a bright area, and then from the bright area you go back to the dark area, or from black to white and then from white back to black, right? So that kind of pulse type behavior, whether it's a square or most of the time it's really like a trapezoid, or as I said, it could be like a very sharp inclination or declination, then that is kind of the ridge that you might call, or sometimes it might be like a triangle like this. Okay, in some literature they call this one a roof. And for these, the edge is like basically, as I said, a bright area separating two dark areas. And you can see that kind of here inside this yellow circle in the image, that you have a dark area here and you have a dark area here, and you have this kind of white edge that is separating them, and that's for which you can see the edge in the edge map. Okay, so anyways, it's a sudden change in light intensity, whether it goes up and stays up or it comes back down. You clearly see this type of behavior. So how can I detect it? Well, clearly I need to do spatial differentiation, right? Because I know if I look at the line, right, where this is the intensity, and let's say this is, for example, the X position, if the behavior is like this, then I say, well, the slope of this line is 2. If it gets bigger, it's 3. If it gets bigger, it's 4, until you go to what? Completely straight up. For this one, the slope, right? So for this one, as I said, the slope di over dx, for example, could be 2. For this one, maybe 3, 4, 5. For this one, it is going to what? Infinity. So by looking at the first derivative of intensity with respect to the pixel position or spatial differentiation, you can look at the areas where the slope is very large. That shows this kind of step type behavior, right? So if I want to take partial derivative of intensity with respect to the x direction, then I use partial of I with respect to x. If I want to do it with respect to y, then I do partial with respect to y. And what's the difference? The difference is this one, basically in here, the light intensity changes in the x direction. So the edge that you have is a vertical edge. So when you go from this x to this x plus delta x, the light intensity changes. Like for example, in this area it is dark, in this area it is bright, or the other way around, right? Or like I of this side is less than I of this side significantly. Then taking derivative with respect to x would show you that the step type behavior. So this, as I said, this partial derivative is good for detecting a vertical edge. This one here is good for detecting a horizontal edge. So when you go from y to y plus delta y, again, your I changes dramatically, right? For example, here is dark, and here is bright. So again, you can say this I1 is much, much less than I2, and so the partial derivative is going to be significant. Now, how do I use what I learned in the previous video, which was convolution and linear filtering? How do I use those? Well, I showed you that if I use kind of this kernel, then this one can do like x derivative for me inside the window of 3 by 3. This one can do the y derivative inside the window of 3 by 3. And these two kernels, I call them the Prewitt kernels, right? So Prewitt kernel can give me what? Horizontal or vertical edges, depending on which one I use. So this is kind of like this. One of the simplest edge detectors is to convolve your image with what? With either this kernel or this one, and look at the result. Now, the one thing you have to pay attention to is the light intensity values are not always this nice and clean. They are not just a constant number without any variations. As you move along the x in a bright region, so if you look here in this bright region, not all the pixels have the shared or have the same light intensity. They have different ones, even if it's a little bit. So if you really look, it's not going to be this clean step behavior. It is going to be what you can see here in this picture, right? So it is going to be step type behavior, but on both sides you clearly have what? A lot of oscillations in the light intensities. And your partial derivative filter should be such that it can work with the noisy data. And we all know when you take derivative from the noisy data, the derivatives will generate very large numbers. So basically, if I apply that, let's say partial of I with respect to x here, where this is I and this direction is x, if I apply that filter to this signal, guess what? Not only you get a huge number at here because you have a big slope, you would also get what? A lot of other local maxima. So your plot might be something like this. Here you might have something a little bit bigger and a bunch of other things. So it's not going to be something clean and nice like what you see here, that you get almost zero on each side and a big peak in the middle because of the change in the level. You get all of these kind of fictitious peaks, and they are because you're applying your finite difference kernel, right, your Prewitt kernel, to all of these small oscillations that happen with high frequencies. Because remember, your di over dx, or partial of I with respect to x, is approximated by what? I at x plus delta x. minus I at x divided by delta x. And even when you go from one pixel to the next, although this whole numerator might not be a big number, but the thing is, from one peak on this noise to the next peak, this delta x here is very, very small, because this is a high frequency signal, this kind of noise. And because of that, although numerator is not big, the denominator is small, the whole thing still can be big. Okay, so how would you deal with the noisy data? Well, first you say, can I get rid of the noise or mitigate the effect of noise as much as possible before I take a derivative? And the answer is yes. What should you do? You definitely will smoothen the image, and that's what we saw in my previous video. You can apply a box filter, or what we call the average filter, or a Gaussian filter, which, if you remember, it acts better than an average filter. So first you apply a Gaussian filter to this, and make it the smooth signal. Then you take the partial derivative. And if you remember, in the previous video, I introduced to you a kernel that combines this Gaussian differentiation together. If you remember, the name of it was LOG, the Laplacian of Gaussian. So this differentiation, you do it through the Laplacian operator, which is like second derivative of I with respect to x plus second derivative of I with respect to y. You apply that to the signal that is already applied to it, a Gaussian filter. So you apply that to a smoothened version of the signal. And the 1D profile of that, this is the 2D function, but if you apply the 1D version of that, which is only one of these derivatives applied to the Gaussian function, the shape of it looks like this. And if you apply this to your signal, it first smoothens the noise, then take a derivative, and guess what? That gives you a big peak where the sudden change in the level of light intensity happens, and everywhere else almost zero. So now if you apply a threshold to this, the only place that will be having or showing an edge is right where it should be. Okay, so that is the LOG kernel that I told you. And let's talk about this LOG kernel in 2D. So the function of this Laplacian and Gaussian LOG in continuous form is what you can see here, right? 1 over 2 pi sigma to the 4, x squared plus y squared over sigma squared. And then this exponential term is here. So the exponential term, as you know, is Gaussian, and when you take derivatives of that with respect to x and y twice, this term here in the bracket comes out. So this term here in the bracket is due to the result of applying the Laplacian operator on the Gaussian function. And if you discretize it, right, because images are discrete entities, then you can replace your x and y with basically I and j, as you can see here. Now when you discretize it, here, as you can see, this is a 5 by 5 filter for this LOG. This is the mesh plot of this function. And when you discretize it, you typically ignore this pi that you see here in the denominator, okay? One other thing about the kernel of LOG is that if you look at some of the coefficients or entries in the kernel, that should be equal to 0, right? So here you have positive 8, and then you have 8 of 1s, If you add all of them, should be positive 16 minus 16 should be equal to 0. And the other thing that you need to do is to apply a threshold to make sure that the 0 crossings of the Laplacian function only will keep the strongest edges. And this kernel is different than the Previt, because in Previt you were only doing first order derivatives. So at an edge, right, you have huge first derivatives. Now for the LOG, at an edge, you will get a 0 crossing really. And you need to make sure, so you're not going to get big peaks, because big peaks only happen in first order derivatives. This one is Laplacian operator, which is a second order derivative, correct? And your edges will be converted or mapped into 0 crossings, right, where your positive derivatives, first derivatives, goes to negative or vice versa. And we need to make sure it's a strong 0 crossing, which means basically there is a big difference between the negative and the positive side. So if you have a 0 crossing that looks like this versus something that looks like that, you want to pick this one, okay? And that suppresses your weak edges and only keeps the strong edges. Here I can show you some of that. So this is your original, if this is your original image Barbara, and if you apply this kernel that I mentioned here, if you convolve your image with this kernel, this is here in the middle is the result of the convolution, or applying the filter basically, right? Applying the LOG. Now, if you see here, there are tons and tons of edges. Are you going to keep all of them? No. Here, you apply some threshold and only keep those edges that are really strong 0 crossing. So now, in this binary image on the right, which MATLAB gives you, only the strongest edges are kept. So here, there are some variations. And you can see a lot of kind of minimum 0 crossing or weak edges, but when I apply threshold, you see they're all gone. Okay, so you definitely need to apply some threshold to get rid of the weak edges and the small variations. You need some significant variations to only get the dominant edges. Now, if the threshold is very, very big, then even some of the relatively good edges will be eliminated. And you can see that here, right? If you look at the arm or the elbow or here, you see there are some edges, but they are eliminated. There is no edge left on them because the 0 crossing was not passing through that threshold, okay? Only if the edge was really dominant between a really bright and a really dark area, that would count. For the case like this, where the edge was kind of, even for us, hard to visualize, then you see those will be eliminated. And if for any reason you see that you're losing a bunch of edges, the best strategy is to bring down this threshold. Okay, if threshold is too high, you're missing a ton of dominant edges that you still can see, but the edge detector didn't give you. You bring down the threshold. Some advantages and disadvantages of LOG. LOG is robust to noise, as we said, because you first apply the Gaussian smoothing, then you take the second derivative. The disadvantages about it is it's not oriented. What does it mean? It means it cannot, like Previt, give you what? Vertical edge versus what? Horizontal. Remember, this one gave you a vertical edge, this one gave you a horizontal edge. But since you are applying the Laplacian operator, and Laplacian operator does not have any direction preference, what this one gives you is a mixture of all different edges. Now, it could be an advantage, it could be a disadvantage, but definitely you cannot provide an orientation of specific categories of edges with LOG. And the other thing is, if you apply to edges that are at the corners, two edges meeting at the corners, or if the edges are very, very thin instead of being really thick, then the actual location of the edge might be a little bit displaced. So instead of showing the edge here, it might show it if 1 or 2 pixels to the left or to the right of where it actually is in the image, or where the edges are meeting at the corner. Okay, so it has a little bit of disadvantage, but in general, LOG is a relatively good and robust edge detector. Now, there is another edge detector that is quite more famous than LOG, and that is the Kenye edge detector. So in Kenye, we apply first order derivatives to the Gaussian smoothened version of the image, and so we form the gradient vector. So this gradient is gradient of Gaussian, as I said, the smoothened version of the image, the components of that, if you show them with fx and fy. Then this gradient, you can give it a magnitude, of course, and an angle. And the good part about Kenye is, when Kenye wants to work on the edges, of course, it finds those pixels for which the magnitude of this gradient is large, right? Definitely it acts like the Prewitt because it is using first order derivatives, but because it applies this first order to the Gaussian version of the image, the smoothened version of the image, it is robust to noise. It definitely goes for large magnitudes of the gradient, and the other smart thing that it does, it also uses the information about what? The direction of the gradient. How? So you know the gradient for any contour, right, of any surface. So if your surface is I as x and y, if you plot the light intensity as a mesh plot of x and y, then it has some contours. And at each point, right, the gradient is perpendicular to what? To the contour at that point, right? So here, if this is the tangent, this red line, this arrow shows the direction of gradient, this one, which is perpendicular to the contour. And what this method does, in the direction of the gradient determined by this angle, it looks at what? It looks at the locations that have the maximum gradient magnitude and only keeps those locations and get rid of the rest. We call this non-maximum suppression, and what's good about it? What's good is it tries to give you thinner edges when the edges are like several pixels thick. If you look at this edge here, it is like 2-3 pixels, sometimes more than 2-3 pixels thick. And for the pixels here, you might have some non-zero values of the magnitude of gradient. It only picks that pixel that is going to have a max. So it only basically picks one of these pixels, and as a result, the edge that you see this method gives you is much thinner than many other methods. And here you can see in this image of the retina, this is the Kenye edge detector on the left, and this is the LOG on the right, and you clearly see that the edges of Kenye are much thinner compared to edges of LOG. Okay, so that's the smart part of Kenny. Also in MATLAB, you have the Sobel and the Roberts, or Sobel you might call, Sobel and Roberts edge detectors. For the Sobel, this is the kernel, any of these two, and for Roberts, any of these two. And what's the difference? Sobel is quite close to Previtt. If you look at it, right? If you look, they are close. One of those kernels is for a vertical edge, one of them for horizontal. This is clearly for a vertical edge. This is clearly for a horizontal edge. The only difference is for Previtt, all of these guys were -1, all of them were +1. Here, you change the middle one to -2 and 2, just to basically emphasize the weight of the pixels that are right next to the center. Okay, and the same thing for the vert. So here, this might give you a little bit stronger results compared to Previtt. And the Roberts are even simpler. The Roberts kernels are like 2 by 2, which is kind of not normal because, as I told you, we typically use kernels that are of size an odd number by another odd number. So what this one does is really looking at, if you have an edge, right? It is looking at 4 pixels on the surrounding of the edge and not the edge pixel itself, and kind of acts like the Previtt, okay, but not exactly, okay? So it is really this one minus this one, and these two would really have no effect. So Roberts is not really my choice of an edge detector if I ever have to go with any, but it does give you some edges. I would personally prefer to go with Previtt or Sobel if I want to do something very simple. If not, definitely LOG, and if you really want better results, you can do what? Kenye edge detector. Here I wrote a simple MATLAB code for you, which show you the result of each and every one of these 5 edge detectors in MATLAB. And I'm using the command edge, so I'm not writing the edge detector MATLAB code from scratch myself. I use the code that is already existing under the image processing and computer vision toolbox. And one of the good things with Kenye is, in Kenye you have a threshold that you can choose. The smaller the threshold is, the more edges you are going to detect. The bigger you choose it, you are going to suppress a bunch of edges, and this threshold is anywhere between 0 to 1. Okay, if you don't specify a number, it goes with its default value. So here, let me show you this result before I finish the video. So here, this is the original image, right? And this is the Previtt, right? And you see Previtt detected both vertical and horizontal edges. So which kernel did it use? Both of those kernels really are used in Previtt to give you the edges. If you put it side by side with, let me see if I can find Sobel, this one, you see the results are quite similar. If you can see, the results are quite similar, and that's because you only change that middle gain from 1 to 2 or -1 to -2. So results of Sobel and Previtt to a good extent are very similar. But if you compare it against the Roberts, you see that Roberts is quite weaker than Previtt, right? If you look, Previtt has a lot more continuous edges compared to what? Roberts, and you see a lot of edges are missing and a lot of weak edges are instead detected. So again, as I said, Roberts is not really my cup of tea, but it is a method in MATLAB. Now, if you compare this one against LOG, which is this one, clearly LOG is showing you more detections, right? And again, between these two, I would definitely prefer LOG because LOG does apply the derivatives to a smoothened version of the image, but Previt doesn't. So clearly, the LOG is a much better detector than any of the three previous ones I mentioned. And now if you compare that against Kenye, you definitely see that Kenye is doing a much better job, because it is using the direction and magnitude of the gradient, and it also tries to connect as many white edge pixels together as it can. So clearly you see that Kenye has done a much more reasonable job than LOG. So again, when I want to detect an edge or edge map for any image, I always go with Kenye edge detector. It is definitely a very strong edge detector, devised by Professor Kenye from UC Berkeley. And here is the effect of the threshold, as I told you. The one on the left threshold is 0.1, the one on the right it is 0.6, and you clearly see when the threshold is high, it barely detects any edges because it has suppressed. Not that it didn't detect, it has detected a ton, but it has suppressed all of them. And 0.1, you probably see a ton of edges that shouldn't be there, because what? Because it hasn't suppressed enough, correct? You see here, when I use the one with Kenye and no threshold, it kind of went with some default threshold, and I would say this default threshold is quite nicer in here compared to the two threshold I have chosen. If you just look at them side by side, you see here I have chosen a bunch at 0.1. Right here with default, a bunch of them are suppressed that are not essential. You can see here, you can see some of them on the forehead and so on that are not really necessary, and 0.6 is clearly an overkill. So if you want, you can play with the threshold, but if you don't know what threshold to choose in the beginning, I would say do not specify anything, just go with allowing MATLAB to use its default value. Okay, so I will put the download link for this simple MATLAB code, although you can write all of it yourself, in the video description. And hopefully this brief video on edge detectors was useful to you, and I will see you in my next video. Thank you so much.